So how do you know how much eyepiece is enough and what you want, depending on what you want to look at in the sky? Well, quite frankly, that's a little bit complicated, but I'm going to try to simplify it a little bit. At least I'm going to, in this video, talk about what you can see and understand that I'm going to be approximating things, and it's going to be biased by my own preferences in the sky and so on. But basically what this video is about is what you can see and what you need to have in order to see that, and what you can do to see it better. I think it's also important to explain that I'm not going to be dealing with astrophotography. That is a subject that, I'm going to be simplifying the subject of visual astronomy, but astrophotography is a whole different ball game. It's like the difference between baseball and basketball. It's played on a different court by a different set of rules, and if you're good at one, you may not be very good at the other, and so on. But to do astrophotography, you need a camera, you need software, and you need a lot of time. If you want to produce those super images that you see on YouTube and on Twitter or Instagram, I guess, and places like that, you need a lot of time spent with the software. Just like good movies from Hollywood or wherever they come from, you not only need a good camera, but you need to spend a lot of time doing post-processing, and that's what the software and the time does for you. I'm not going to talk about that anymore. Instead, I'm going to concentrate on visual astronomy. Now, I'm going to immediately pass over the use of go-to scopes. Now, a lot of what I'm going to talk about applies to use of a go-to scope, but a lot of what I'm going to talk about for the next few minutes only has to do with when you are using either a manual telescope or a pair of binoculars or just an unaided eye to see things in the sky, and you want to find things. Well, to find things in the sky, you need some guide that helps you to find the objects. Now, obviously with the moon, the easiest guide is just to use the old Mark I eyeball. If the moon is out, you'll see it. So even if it's cloudy, you can still see the moon behind the clouds in most cases. When you start looking for the planets, though, you really do need something like sky maps. I talked about this in the sources video, astronomy sources, these sky maps that you can download from the internet. A viewer has also pointed out that there is an Android app available from, I think, the Google Play Store that I think it's also called Sky Maps, that you can download to an Android device, and it will show you. I'm sure there must be something similar to that for Apple devices and so on. Something that is very useful is a program called Stellarium. So let me show you that one. Here is a view of Stellarium, the program. You can download this on the internet if you just go to Google and type in Stellarium download, Stellarium 0.19.3. So what it is, or what it does, is it displays on your computer the night sky, the sky. You can set the time anytime you want. It's middle of the day here, but I have it set to this evening. And you notice that there are a couple of stars. Here is one of the bright stars, Sirius, another bright star, Canopus. People often call these guide stars. But the main reason I wanted to show you this is you can get an idea of what's available for free over the internet in terms of a guide system for finding your way around the night sky and learning where things are and so on. Similarly, when you are looking for deep sky objects, stellarium can be useful as well. But I suggest that you get a star atlas if you're interested in looking at the deep sky objects, partly because, I find something like the Cambridge Star Atlas to just be more convenient to use. And if you buy them used on places like Better World Books, they're not that expensive. One of the things that you need to consider is the type of mount that your telescope has. A lot of telescopes have altitude azimuth mounts these days, and let me zoom in a little so you can see a little better what I'm talking about. And one version of Altaz, called a Dobsonian, is actually a very economical and, quite frankly, rather pleasing mount. I don't own a Dobsonian, but I have used them, and basically you just move the telescope around in altitude and azimuth. A good Dobsonian mount has really smooth bearings, and it can be really neat looking around the night sky with a Dobsonian. But one thing you'll find is that it does not, you really need to be able to star hop. And I'm not going to talk about that here, but if you want to find particular things in the sky, you need to be able to find a guide star and then hop from that one to another star and so on. Something that, if you are interested in that, look for star hopping on YouTube. There is a real good series from the Kissimmee Peak Observatory that I recommend. I prefer a polar mount, sometimes also called an equatorial mount. And one of the reasons I prefer that is it allows you to use what are called setting circles. And frankly, I'm so familiar with that method now. I've been at this a long time, and like most dinosaurs, I'm pretty much stuck in my rut. So I find it rather pleasing to use a polar mount or an equatorial mount telescope, in particular the Meade LX10, with setting circles. So let's take a look at setting circles at this point. On a telescope without a go-to system, there is a method for finding your spot in the sky, and it's called setting circles. Here is a setting circle, and by the way, I'm using a red flashlight here because that's what you should use at night when you're doing this. This is the setting circle for declination. That is, how far away from the celestial equator. It's the equivalent on the surface of the Earth of your latitude. In other words, how far you are north or south of the equator. Well, in the sky, there's an equator as well. And so this is the way that you set that. I know this is going to be a little hard to see, but on this particular telescope, what you do is once you know the declination of where your scope is pointed to, and by the way, right now I have it pointed down at the ground. Obviously, that's not where it would be in the sky, but I did that for a reason you'll see in a second. But what you do is you set the declination of the object that you're looking at, and then you tighten this down. Once it's tightened and it's properly set, let me show you where you set it. There you see is a guide that you set your declination to. So in this case, the declination is set to, looks like about 12 degrees. That sets one axis. The other axis is set by what's called right ascension. And that setting circle is here. So let me come around on the other side and also put a little more light on it so you can see what that's about. Okay, here is the setting circle on the for right ascension. That basically measures time in the sky, just like longitude on the surface of the Earth measures time. And if you know the history of longitude, you know that the most important thing for you to know is what time it is if you want to determine your longitude. So once again, there is a spot that you see right here with an index mark. And what you do is, once you have the right ascension of the object you're looking at, you set it on this setting circle. Then you don't touch that setting circle, and I'm going to try to do this without upsetting the scope too much. Then as you notice, as you turn the scope, that index mark moves around, but the setting circle stays where it is. Now, it's not actually staying still, because the motor drive of the telescope is actually driving that setting circle, and as a result, once you have locked the right ascension, which is what this knob on this scope does, then as the telescope tracks the object, it maintains the same right ascension, because every object in the sky has a declination and a right ascension. Now, for things like planets that move fast, the declination and right ascension can change quite a bit on any given night. But for most objects, stars, Messier objects, and so on, the right ascension and the declination is basically the address. They stay there, and once you know what that is, and once you have your scope set properly, you can go to any object in the sky using right ascension and declination. So I hope this is helpful for those of you that do not have go-to scopes. Now, a go-to scope does all of this for you. It knows the right ascension and declination. It also knows where to point your scope to get to that place in the sky once you have properly calibrated the scope or aligned the scope with the sky. But the same process happens with these manual scopes. That is, you first align your scope with the sky, setting the polar alignment, the declination index, and the right ascension index until those are properly set. And once they are set, then you can, to a reasonable degree, find objects in the sky by simply adjusting your telescope. Now, obviously, if you move your telescope, then you have to reset the settings, same as what you have to do with a go-to scope. So anyway, I thought this might be helpful and useful for people who, even if you have a go-to scope, you might want to think about the use of setting circles, because it'll help you learn a little bit about navigating in the sky. Okay, we're back now to the question of a telescope type and the eyepieces that you want to use for that. If you watched my earlier video on types of telescopes, you know that refractors are the original the Galileo types, and they have a lot of advantages, and I know a lot of people who swear by them. They can be expensive when you get good ones, but some people think that that's really the only kind of telescope you should have. They certainly have very low maintenance. I prefer reflectors, and I have over the years used Newtonian and Cassegrain. Cassegrain come in a variety of versions, Maxitov Cassegrain and Schmidt Cassegrain and so on. those are what I tend to use, and that's what the LX10, the Meade LX10 is, as well as the Celestron 8SE that I recently purchased. When it comes to eyepieces, there is a difference between what you might want to use for the moon and what you might want to use for the planets. Also, I'm going to talk about deep sky objects because that's really the field that I enjoy the most. But before I do that, I would like to cover a couple of things about eyepieces and optical tubes and so on. My belated attempts at drafting here. This is my feeble attempt to show a human eyeball. The purpose being that the average person can see a field of view of approximately 160 to 170 degrees. But when you look through a telescope, remember, you're looking at the sky through a pipe. And what that means is that no matter how wide your eye can see, the pipe restricts how much sky you can see through this optical tube. And whether you put lenses here or eyepieces here or whatever, you are limited by that. Another thing that you are limited by is what is called the exit pupil or the pupil size of your eye. And a dark adapted young eye can have a pupil size of 7 millimeters. Most people that are more than 20 or 25 years old only can go to about 5 millimeters, and that's when the eye is dark adapted. So you're limited by what you can see through a telescope tube, and you're limited by how big your eye can open up. And the reason that is important is because of what is known as field of view. Now, the actual field of view, or what you might call the optical field of view, is what you can actually see with your eye and the eyepiece you're using. Now, if you use a very long focal length eyepiece, it doesn't do you any good, because the focal length of the eyepiece determines to some extent what the field of view is going to be. And if you have too wide a field of view in the eyepiece, what you're actually looking at is the sides of the tube that you're looking through. So let's talk about that a little bit more. And by the way, the optimum field of view for a 2,000 millimeter Schmidt-Cassegrain is an eyepiece of about 30 millimeters. The reason is, at a 30 millimeter eyepiece, you just see to the very edges of the tube, but you don't see a lot of the tube itself. So here is an example of a very wide angle. Meade calls it ultra wide angle eyepiece. Now, these get pretty expensive, and I certainly don't advocate that people starting out buy these kinds of eyepieces. Wait until you see that you're really interested in astronomy and you really like to see. This particular eyepiece is pretty good for looking at deep sky objects. It has an 82 degree apparent field of view. It is a 20 millimeter eyepiece. So if you divide this 20 into a 2,000 millimeter focal length like a Schmidt-Cassegrain, that is where you get the power or the magnification that this eyepiece will produce. Similarly, if you divide this 82 degrees by whatever the power is, and of course you need to know the size telescope you're using to compute the power. But once you know the power or the magnification, then you divide that number into this 82 degrees to determine the actual field of view. Unfortunately, they don't say that the A here stands for apparent. Once you put this on a telescope, you only get a field of view that is as wide as this divided by the magnification of the telescope. Now, one other thing that I mentioned is a focal reducer. And this is a focal reducer. It reduces an F10 Schmidt-Cassegrain to an F6.3. It also widens the field and flattens slightly. It flattens to some extent. It doesn't make a perfectly flat field, but it makes the field flatter, which is very important for astrophotography, but not so important for visual use, especially if you're just looking at the center of the image. But nonetheless, this is the corrector and reducer that will allow you to reduce the effective focal length of your Schmidt-Cassegrain telescope. At least it's the one that I use, and there are others available out there. Meade makes one, and I think Orion sells one, and so on. Now let's talk about eyepieces for a Schmidt-Cassegrain. And I'm going to mainly focus on the planets and the deep sky, mostly deep sky. First, let's be sure we understand that power and magnification are just two words for the same thing. If you take the size of the objective lens in millimeters and divide by the size of the eyepiece in millimeters, you get the power or the magnification. So let's look at some examples. If you have a 2,000 millimeter Schmidt-Cassegrain, for example, and this is true of all telescopes, but I'm just using Schmidt-Cassegrain because that's what I tend to prefer. If you have a 2,000 millimeter objective and you put a 10 millimeter eyepiece in it, you will get 200 power. That's usually called high power. If you instead put a 20 millimeter eyepiece in it, you'll get 100 power, kind of medium. If you put a 40 millimeter, you'll get about 50 power, or medium low power. If you put a corrector and a 50 millimeter eyepiece in, you can get down to 25 power, which is considered low power. Now, for the biggest deep sky objects, that is, the ones that occupy the biggest space in the night sky, this is about the only way you'll be able to see the entire object. So there are some Messier objects, for example, and nebula, galaxies, and so on, that to get to, if you have a 2,000 millimeter Schmidt-Cassegrain and you want to see the entire object, you pretty much have to have a focal reducer to get the effective focal length down to about 1,250 millimeters, and a very wide eyepiece, or I should say a very long focal length eyepiece, so that you get the power down to 25. Now let's talk about another thing that's important called field of view. Every eyepiece has an apparent field of view. If you remember, when we were looking here at the eyeball, that the apparent field of view of your eyeball is probably 160 or to 170 degrees. But most eyepieces, particularly the ones that come with telescopes today, fairly good telescopes, but not really expensive eyepieces, have apparent fields of view of 50 degrees or less. So in other words, about a third of what you can see with your eye, you can see through an eyepiece, irrespective of what telescope you put it into. If you take the apparent field of view of the eyepiece, and the only way you can know that is to read it off the eyepiece, and divide by the power, that is the power that we calculated up here, that will show you the actual field of view. Let's look at an example. If you take a 50 degree eyepiece and a Plössl A good Plössl has about a 50-degree apparent field of view. And suppose you have a 20 millimeter Plössl, so about 100 power. You divide the 50 degrees by the 100 power and you get a half a degree, which is about the size of the moon, the full moon. If, on the other hand, you have an 80-degree eyepiece, like the Meade 20 millimeter, and you're using it at 40 power, and notice here, that means a 2000 divided by a 32 millimeter, I think is what I used for this. Then you get a full 2 degrees. There are many deep sky objects that are nearly, or some a few more than, 2 degrees across. So, if you buy an expensive eyepiece that has an 80-degree apparent field of view, and you use it in a telescope such that its focal length and the telescope's focal length give you about 40 power, you'll see about 2 degrees of sky. That's the actual field of view you see. Now, what do you really need in terms of eyepieces? Well, for the moon, you want to use either low or high power, because low power shows you the whole moon. High power shows you very sharp details. And the moon is bright enough that you can get a pretty good view even with a high-powered eyepiece. So if you want to really look carefully at the details on the moon, the big problem with the moon is contrast more than brightness. And to lower the brightness, you might need to use a neutral density filter, which I talk about in some of my couple of videos on filters. But if you haven't heard of a neutral density filter, it's a fairly low-cost addition to your viewing, and if you do very much moon viewing of the moon, you'll probably want to get one. For planets, you generally want to use high power, from 200 to 400x. Now, and you don't really care too much about the field of view, because you just want to see the planet. And very few telescopes are capable of enough power, given normal seeing, that the planet will be too big for your eyepiece. So the narrow field of view is fine. In other words, what I'm saying is, if you have a 50-degree Plössl, it'll work fine. The main problem with planets is getting enough power given the seeing. Now, depending on the size of your telescope, most 8-inch Schmidt-Cassegrains can handle 400 power. But a 4-inch, for example, you probably should stay down in the 200 to 250 power range, because you're limited by 3 things. The relative focal ratio of the telescope and the eyepiece, the size of the objective of the telescope in terms of being able to get maximum resolution, and the seeing conditions that particular night. If the seeing is bad, you'll be lucky to get away with 200 power. So, but if the seeing is great and you've got a fairly large objective, like an 8-inch or so, you can use up to 400 power generally on planets. In the deep sky, just the reverse. You want lower power. Generally, you'd like something between 25 and 50. And you want as wide a field of view as you can afford to buy. So eventually, what you will discover, I think, is, at least conclusions I have drawn, is if you're primarily interested in visual astronomy, and you want to look at the moon, the planets, and the deep sky, your selection of eyepieces and of your basic telescope, including the type of mount and the type of guidance, will determine how well suited your setup is to that particular thing. I suggest that you try to do a little of all of these. Look for some deep sky, look for planets, look at the moon. And with time, you'll come to realize what it is you prefer the most. And then you can start focusing on some of these more esoteric issues, like the field of view of your eyepiece and the effective power of the eyepiece and so on. But I hope that in general, this gives you an idea of what the factors are that you need to understand. I suggest if you want a little more on this, or just the view of a different person, that you go to the Orion Telescope's website and look for a video called Choosing Your Eyepiece. That may not be the exact title, but it's close to that. So I hope you've enjoyed this. I hope that you'll find things in the night sky that you really enjoy looking at. And as you build up to a good telescope with some good eyepieces, maybe a few filters and that kind of thing, that you come to feel that you haven't wasted your money on a bunch of trivial things that you no longer use, but instead have sort of built your collection in a prudent, I would say frugal manner. So, hoping that you'll have clear skies, and stay tuned for some more videos. In the meantime, have a nice day.